In this module, we want to talk briefly about the mechanical properties of polymers. Now, I know in this class we're not really focusing on mechanical behavior because that comes in the follow-on class, but there's some critical features about polymer mechanical properties that you need to be aware of because it comes into play elsewhere as we're going to define things like the glass transition temperature. So typically mechanical behavior can be grouped into three different classes. The first class is what we call brittle elastic, and it just looks like a straight line elastic curve, and then it fails abruptly. The second class is elastoplastic, so it initially loads up elastically, it yields and then plastically deforms, and then finally it ultimately fractures. And then finally, there's elastomeric, which is actually a nonlinear elastic material where it's a relatively low modulus until you get to very high strains, and then it finally fails. One thing to note as you look at this graph that I'm showing you here is that the strains go from not in 1%, these go from that's 100% strain, 200% strain. So very different than what you expect in metals, but also lower stresses than you expect in metals. So just to give you, to kind of locate polymers for you in terms of where their properties lie, their elastic modulus, and they still have an elastic modulus, just like metals do. But their elastic modulus is typically lower than metals, somewhere in the range of, let's say, 7 MPa, not GPa, MPa, up to about 5 GPa. And there's some special cases where if you look at, let's say, Kevlar fibers, or if you look at ultra high molecular weight polyethylene or something like that, in fiber form, they can get higher than that. But this is a general, these are generally a good range to think of polymers in. Okay, similarly, the tensile strength is only maybe about 10% that we'd see in metals, and that might range somewhere from 1 MPa up to 100 MPa. The property that's significantly more than metals is the fracture strain, or the strain to failure, and it's going to range from maybe 1% all the way up to 1,000%. So those are kind of the differences between polymers and metals in terms of properties. But there's one other really important way in which these properties differ, and that's that mechanical properties of polymers are going to be highly temperature sensitive in a way that we just didn't see in metals or care about. So how do they work? Well, what I'm showing you here is a plot of just a stress strain plot for PMMA, that's polymethyl methacrylate, which is just you know as plexiglass. And so this blue curve shows sort of that brittle type behavior we were talking, and that's occurring at 4 degrees C. As we heat the material up, we start bending around till at 60 degrees C, we're now observing the elastoplastic behavior. So a single material, depending on the temperature, can actually take on multiple mechanical characteristics from the classes that we talked about previously. So we can kind of look at this curve. This is, again, we're going to use it as a kind of an example for polymers in general, but as a general rule, with increasing temperature, our modulus will decrease, our strength is going to decrease, but our elongation to failure is going to increase. And embedded in this is a little, so let's maybe back up, I guess, and say the reason for this is that at low temperature, the polymer molecules are not very mobile, and so they can't uncoil or respond to the load, and so they act in a very stiff manner. That's why you get this blue curve. In contrast, at higher temperatures, they have enough mobility to respond and extend themselves. The chains can uncoil or whatever in response to the load that's being applied, and so they're able to deform much more readily at lower stresses. So you can think of that as if there's a temperature dependence, and there probably is also a dependence on strain rate. So if we load it fast enough, even at some temperature that we'd maybe seen previously, gave us elastoplastic behavior. If we load very fast, then we're going to still load faster than the molecules can respond, and it'll give us a low temperature response. So with increasing strain rate, we're going to see a modulus increase, we're going to see a strength increase, and we're going to see an elongation to failure decrease. So the idea here is that an increasing strain rate acts on the polymer in the same way that a decreasing temperature does. So polymers in general are going to be very sensitive in terms of time temperature effects. So now let's talk real briefly about some of the mechanisms in these features, in these polymers rather. So this is for the brittle failure mechanism, and those are going to, in general, depending on the temperature still, but across the board, usually aligned cross-linked polymers and network polymers are going to show this type of behavior. So in the case of an aligned cross-linked polymer, we have chains that are aligned and then they're cross-linked, and as we load up, those chains get stretched. So we're basically stretching the covalent bonds. That gives us a pretty stiff response. We know covalent bonds are very strong. Um, in, and similarly, a network polymer begins as this network state, and we just stretch those covalent bonds of the cross-linked network, and they stretch and or bend. So that's why we get a brittle response that has a high modulus, high strength, but low strain to failure. Now let's talk a little bit about the elastoplastic mechanism. And we're going to specifically focus on semicrystalline polymers here. So we begin with some undeformed structure that has some amount of crystalline polymer and some amount of amorphous polymer in it. And during the first stage of loading, the amorphous regions are going to elongate. The next stage is that the crystalline regions are going to align, and then the blocks of the crystalline regions are going to separate, and then those are going to also grow into like a fibrillar structure. So that's sort of the features on what drives this elastoplastic deformation in polymers. Now, in the elastomeric case, remember elastomeric, we said this before, but I'll remind you, you have to have chains that are kinked and cross-linked to get elastomeric behavior. And so what you have is a coil of chains, but the chains are cross-linked. And so, and remember that elastomeric behavior is reversible. So it needs something that has to go up and then back down the same curve. And what's really happening is that those chains uncoil and stretch out. And then as they get straighter, they get stiffer because you're now pulling on them, pulling on those covalent bonds. And if you let off the load, the cross links in between the chains will tend to pull that that structure back into its coiled structure, and that's why we get this elastomeric behavior. Okay, one final topic I wanted to cover. Again, you'll cover it more carefully and thoroughly in your mechanical behavior of materials course, but at least to give you an introduction. In some temperature range, polymers display some combination of both liquid, which is viscous, and solid, which we'll call elastic behavior, simultaneously. And so when we're in that region, we call that viscoelasticity. And we can observe that by applying some fixed strain epsilon naught and holding it. And what we're going to observe is a decrease in stress. So that's what I'm showing you on this curve here. Here's the time and here's the stress. If we load up in this blue curve in strain and we just hold for as long as you want, the stress will initially follow elastically, but then there'll be a decrease as the polymer viscously flows to accommodate that strain, and then the stress will decrease. We quantify that by what's called the relaxation modulus, which is just the stress as a function of time divided by that applied strain that's fixed. And a lot of times in polymer properties, you'll see this relaxation modulus reported. So I want to show you what that looks like as a function of temperature, because it's very important. So here, this is for amorphous polystyrene, and I want you to just take a look at this this y-axis. So we have, let's say this is maybe at a little bit below 10 to the 4 megapascals, and all the way down to 10 to the minus 3 and below. So we have almost 7 orders of magnitude in that relaxation modulus change as a function of temperature over a relatively small temperature range, going from only maybe 60 to up to 200 degrees or so. And so what we basically can broadly categorize the behavior in 3 different regions. The first is this low temperature region where the polymer primarily acts as a rigid solid, we just call that's mostly elastic. If we get to very high temperatures and the modulus goes way down, it's mostly acting in a viscous manner. Uh, so it's going to flow more like a liquid at that point. But then there's this transition region that is where we have viscoelastic behavior. So those are the kind of the highlights of the mechanical behavior of and properties of polymers that I want you to be aware of before we move on to talk about things like the glass transition temperature, melting, processing, those kinds of things.